Somewhere in our galaxy right now, the laws of reality are collapsing. It's an object with no surface, no exit, and a hunger that defies the very fabric of space. We've photographed it, we've measured it. But there is one fundamental truth about it that physicists are currently terrified to admit. They have no idea what happens when you actually cross the line. And if you think you're safe because you're millions of light years away, you might want to look closer at what's lurking in the dark. There are an estimated 40 million stellar black holes in the Milky Way alone. And that's just the small ones, the remnants of dead stars, each one between 5 and 100 times the mass of our Sun, scattered silently through the same galaxy where we sleep, eat, and live our small, ordinary lives. At the center of nearly every large galaxy, including ours, sits something far worse, a supermassive black hole, billions of times heavier than the Sun, ancient beyond comprehension and almost certainly awake. In April 2019, the Event Horizon Telescope collaboration released the first image of one. It looked exactly like what your nightmares would design if your nightmares understood physics. To understand a black hole, you first have to understand what breaks. Gravity, at its simplest, is a curve. Einstein showed us in 1915 that mass bends space and time like a bowling ball on a rubber sheet. The Sun bends space enough to keep planets in orbit. But a black hole? It doesn't just bend space, it punctures it. The curve becomes infinite. At the event horizon, even light, the fastest thing in the universe, is trapped. But don't let the math fool you. This isn't just a theoretical boundary. It's a point of no return where reality itself becomes a one-way street. Now it gets stranger. Time itself begins to break. Near a black hole, time slows down. This isn't science fiction. It's a measurable fact. A clock near the horizon would tick significantly slower than one far away. Near a supermassive black hole, this effect is so extreme that you could watch the entire history of the universe play out in fast forward while you experience only a few seconds. But if you tried to get close enough to witness that, you'd face something far more personal. Then there is spaghettification. It's a ridiculous name for a horrific death. As you fall in, gravity pulls harder on your feet than your head. You are stretched into a single strand of atoms, threaded into the darkness like silk. You wouldn't feel it. Your brain would stop processing reality long before the process finished. But the fact that physicists had to name this effect should tell you everything about the nature of these monsters. Yet the physical destruction of your body is the least of our problems. The real mystery isn't about what happens to you, it's about what happens to the universe itself. Everything that falls in, every atom, every photon, every bit of information appears to vanish forever. But here is the clash. Quantum mechanics tells us that information cannot be destroyed. It's a universal law. And yet Hawking's math says black holes evaporate, releasing only chaotic energy, not the data they swallowed. This is the black hole information paradox. Two of our greatest theories, general relativity and quantum mechanics, are staring at each other, and they completely disagree. Something is fundamentally wrong with our understanding of nature. We just don't know what it is yet. The idea of a black hole is older than the telescope. In 1783, an English clergyman named John Michell sat down and calculated something extraordinary. If a star were massive enough, its gravity would be so strong that light itself couldn't escape. He called it a dark star. Nobody took him seriously. The mathematics was correct. The concept was simply too strange for the era. More than a century later, Carl Schwarzschild solved Einstein's field equations from the trenches of World War I in 1916, literally while fighting on the Eastern Front, and produced the first exact mathematical description of what we now call a black hole. He mailed the solution to Einstein. Einstein was stunned. Schwarzschild died months later of a disease contracted at the front, never knowing what his equations had revealed. The boundary of a black hole, the event horizon, is still formally called the Schwarzschild radius. The universe has a long memory. So what actually happens inside a black hole? Here, physicists split into factions. The first interpretation is the classical one. You fall in, and everything compresses toward the singularity, a point of infinite density at the center where our equations break down entirely. Breakdown here doesn't mean the math gets complicated. It means the math produces infinities, which is physics' way of saying we don't know. General relativity, the theory that predicts black holes so accurately, cannot describe what happens at the singularity itself. It simply refuses to. The second interpretation comes from quantum gravity theorists who argue that the singularity isn't real, that it's a symptom of using the wrong theory, like dividing by zero. In their models, matter doesn't compress to a point. It reaches a state of extreme density, bounces, and potentially creates what some call a Planck star, something that could, in theory, explode outward again billions of years later as a white hole. This remains entirely theoretical. No white hole has ever been observed, but no one has ruled it out either. The third interpretation is the most disturbing, the firewall hypothesis, proposed in 2012 by physicists Ahmed Al-Maheri, Donald Marolf, Joseph Polchinski, and James Sully. Their calculations suggest that the event horizon isn't the gentle, invisible boundary Einstein's equations describe. Instead, an infalling observer might encounter a wall of high-energy radiation, a firewall, the moment they cross the horizon. Instant incineration. This would violate Einstein's equivalence principle, one of the foundational assumptions of general relativity. Either quantum mechanics is wrong, or general relativity is wrong, or both are wrong in ways we haven't discovered yet. All three possibilities are, to put it mildly, uncomfortable. The honest answer is that we do not know what happens inside a black hole, and we may never know because nothing that crosses the event horizon can ever send information back. There is something quietly humbling about black holes, not because they could destroy us, but because they reveal the edges of human understanding so cleanly. We built civilization on the assumption that with enough time and enough intelligence, everything can be known. Black holes suggest otherwise. They are places where our best theories fail, where even the concept of what happens next may not apply. And yet we found them. We photographed one. We named the boundary after a soldier who solved an impossible equation while the world burned around him. That feels important, not as a warning, but as a reminder. The universe is not obligated to be comprehensible to us. It is not designed for human comfort, human scale, or human time. And yet here we are, a thin film of life on a pale blue speck, looking outward with our instruments and our mathematics and our stubborn curiosity, mapping the edges of the unknowable. Every black hole in the sky is a door we can approach but never open. and somehow the approaching is enough. Thanks for watching, and subscribe for what we discover next.